Okay, welcome to Poly Day 9. Today we're going to talk about comonoids in Poly again, and then talk about, and I'm going to call the category of comonoids in Poly cat sharp. Then we'll talk about the differences and similarities between cat and cat sharp. This is the category of categories. This is comonoids in Poly. And then we'll talk about Cofree comonoids. And so last time we talked about what a cofunctor is. And so if you have, and I'll just review that. So if you have two categories, C and D, then a cofunctor between them is some kind of mapping. And all it is a homomorphism of comonoids. And that says you have a map of polynomials from C to D. And when you apply the epsilons, it commutes. And when you apply the deltas, it commutes. But if you remember, how do you go from a category to a polynomial? Maybe I should have written this. I'll write it here. So if you have a category C, you would define little c to be the sum over all the objects of your category of y to the maps out. So C bracket I is like the choice. It's a choice of all I prime in ob C and a map in C from I to I prime. So you just take all the maps out of your object I, and that's what you put upstairs there. And so this is saying that for every object of C, I get an object of D, and for every map out of that object in D, I get a map out of that object in C. So I've just taken this definition of homomorphism between comonoids and written it for categories. So what is a cofunctor between two categories? It's a function from objects of C to objects of D, and then for every object of C, a map from the image object in D to some other object in D, call it J prime. For every one of those, a choice of some map from I to some I prime in C. So for every map out of the image object in D, a map out of the object in C. And that thing should preserve identities, codomains, and compositions. So the pullback of some map, if that map was the identity, it should be the identity. If I pull back some map and take its codomain and push it forward, that should be the J prime I started with, the codomain of the map. And if I take some map and pull it back and then compose with the pullback of some second map, that should be the pullback of the composite maps. So it does what you want. It just varies, like it makes sense. It's just kind of strange to be pulling maps back. And that strangeness is what I'm going to go over in part one, is like how you think about this with a bunch of examples. So I'll talk about cat sharp. And cat sharp, again, is just the category whose objects are categories and whose morphisms are cofunctors. OK, so let's talk about cat sharp, just some things about cat sharp. So in cat sharp, comma, 1, y is terminal. Y is the category with one object and one map out. So it is the category that you would normally call 1. And it's terminal because if I had some other comonoid or category, then I already have this epsilon map to Y, and Y has an epsilon map to Y. And that thing over here is the identity because there's only one map from Y to itself. And so this thing has to be epsilon for this to commute. There's only one possible map from C, cofunctor from C to Y. 0 is initial. Because basically, there's only one polynomial map from 0 to C. And so there's and that thing is a cofunctor because it satisfies all these things trivially. For each I is a vacuous condition. 3. Well, we can talk about cofunctors into AY. Nelson, a few days ago, talked about how if A is a set, then AY has only one possible category structure because it's saying that this has A many objects and every object has one map out. And if you're going to be a category, of course, that one map out has to be the identity. But you could say, what are cofunctors into AY? And here's a fact. Cat sharp maps from from C to AY are just set maps, just functions from C of 1 to A. So it says if you want to have a cofunctor from any category to AY, it's just labeling your objects with elements of A. C of 1 is the objects of the category C. Okay, this one is, let's get a little bit more interesting. So I'm saying there's an adjunction here, by the way, but that's not too important. And it's not too important because this is a part of a more general story we'll talk about later when we get to Cofree comonoids. This is going to say that AY is the Cofree comonoid on A. But here's something a little bit more interesting. Cofunctors into y to the n, y to the z, and y to the q plus. So Nelson a few days ago told us that if this thing, like y to a set is actually a comonoid, if and only if that set is a monoid. So a monoid structure up here will give us a comonoid structure on y to the that thing. And so in other words, that like these y to the something is a one object category, and so of course we, or maybe not of course, but you may know that one object categories are exactly monoids, and monoids, and so this might not be surprising if you think about it that way. And so what is a cofunctor from C to y to the n? This one will give us most of what we want to think about for the other ones. So we have this C thing. So we have C, and we have y to the n. And y to the n has only one object. So a map like this is no data here, but then it takes any object in C and any natural number in n and gives us something we could call I dot n. And so for all C, let's see, for all objects in C1, I dot n is a map out of C. And let's write I dot n for its codomain. So what we're saying is that for every object in C, we get this map out of it, and every natural number. For all this and all natural numbers, we get this thing. But we know some facts. We know that when we take the identity on n, which I'm sorry, I didn't say this, but I want n to be the monoid n0 plus. And in all these cases, I'm using the additive structure. So what I'm saying here is we know that I dot 0 is the identity. And we know that I dot 1, when we look at its codomain and then dot it with 1 again, well, let me do it more generally. I dot m dot n is I dot m plus n. That's what this one here says. And so this one is vacuous because there's only one j prime there's only one object in this thing, so it's not telling us anything. But what I'm saying here is that if you go m steps and then you go n more steps, it's the same as going m plus n steps. And so what this kind of tells you is that it's all determined, well, it's not kind of telling you this, it is telling you this. I dot 1. If you knew I dot 1, you could get I dot 50 by just dotting 1 50 times. And so what we're saying is that this is given, so cat sharp maps from C to y to the n is the same thing as polymaps from C to y. Now, I've abused notation here because this C over here is really C and some comonoid structure, and this C here is the underlying polynomial. But the point is, this is again going to get us to this Cofree comonoids. We're saying that y to the n is the Cofree comonoid on y. We're not ready to tell you what that is, but that's what this adjunction, this sort of symbol or this sort of equation is going to tell us. But the point is, we can see why it's true because the entire thing, if we have a cat chart map like this, a cofunctor from C to y to the n, it would be completely determined by where it sent the one guy. So what is this thing? It's kind of like a direction field. So cat sharp C y to the n is a direction field. I guess I'm defining direction field right now on the category. It's this, you have this category. It's got lots of objects and morphisms whatever, all sorts of stuff. And for every object, you're picking one morphism out of it. Okay. But, okay, that's interesting, I guess. It actually is interesting when C was, like, remember we had this, like, if X was a metric space, we had this thing like sum over points in X of Y to the curves in X. This would basically be picking for every point a curve coming out of it of some length. And that, if we worked in a topos besides set, you could actually ask that this was continuous. Like, given nearby points, the curves coming out of them would be close. Okay. Okay, then what is a map in cat sharp from C to Y to the Z? Well, it's basically, we would get like this I dot 1 just like before. But we'd also get I dot negative 1. And we'd know that I dot 1 dot negative 1 would have to be identity on I. And I dot negative 1 dot 1 would have to be identity on I. And so what we're saying is, in this one, we had two arrows coming into the same dot. But if we had to, for every one of these, pick some arrow coming in instead of just all the arrows coming out. Like in this one, we just pick one arrow coming out. Here we have to pick an arrow coming in and an arrow coming out. The arrow coming in will be this one, and the reason I know it's an arrow coming in is because, this one. The reason I know it's an arrow coming in is because as soon as I hit it with the arrow coming out of that thing, I get where I started from. So, and the other one says that basically they have to be invertible. So if two of these came in, and I said, now I need a map, I need a negative 1 guy, and I picked like this guy. Sorry, I have to pick an arrow coming out, so it has to be the inverse of this one, I guess. And then when I go back and then forward, I have to get to identity on this thing. Anyway, so it basically makes my direction field not have any collisions. It'll just have everything will have exactly one arrow into it and one arrow out of it. And then what is cat sharp of C y to the q plus? Q plus is the rationals under addition. Well, I'll get things like I dot 1 over n for every n. And I'll get this. I'll get that if I do this, 1 over n, 1 over n, lots of times, that's I dot 1. So it'll force me to like not only be able to pick these little arrows, but also be able to subdivide them as much as I want. So if I had this curvy thing, it would say, oh, at this point, I'll pick this curve. I have some metric space, whatever it looks like. And then I'm at some point, and I say, oh, this is what I get for length 1, C of 1. And then I say, well, what do I get after length 0.5? Well, it'd have to be something along this curve, because if I go for 0.5, and then I go for 0.5 more, I have to get this exact curve. And so for 0.25, I must have gone, right? It has to just subdivide more and more. Okay, so it's just kind of saying, for any amount of time I want to look at, as epsilon approaches 0, I still know how far, exactly what curve I traveled through. So it kind of tells me the integral of the vector field. Instead of giving me a vector field, it tells me how to integrate it for any amount of time. So in some sense, this is maybe what you actually want to have. It might not be what you want to give. If someone was to give you a vector field, they just have to tell you some differential equations. Those don't take much data. But if you wanted to have a vector field, you'd want to actually have what it does often, like how you integrate it. And so this is emphasizing what you want to have rather than what you want to give. But it's still, you can give one of these using a differential equation or a system of differential equations. Okay, let's see. Wow. Discrete op fibrations. A discrete op fibration, this is it's a long word with an easy definition, is a functor C to D such that for all I objects of C, the map C bracket I to D bracket F of I is a bijection. Meaning, if you have a map out of I and C, you get a map out of I and D, of F of I and D. And if you could take any map out of F of I and D and give yourself a map out of I and C, and that was invertible, that would be called a discrete op fibration. So if I had a discrete op fibration, that's a functor, but it's also a cofunctor. Discrete op fibration is also, or a it isn't quite a cofunctor, it's a functor. But how do I get a cofunctor? Well, I just need a map from D of F of I back to C bracket I, and I just take the inverse of that, of this one. So this was a bijection, so I can just take the D bracket F of I thing and go to C bracket I. And that will, yeah. Okay, so that's another way you get cofunctors. Here's a good one. So what is a cofunctor? Remember, we have these s y to the s things. Another way to write this is ss. This is called the store comonad in Haskell, or the co-state comonad, or the state comonad for state set S. And here's this one. And what's a cofunctor from sy to the s to ty to the t? Well, first of all, it's a polynomial map. So it includes a phi of one thing and a phi sharp. I didn't write those so carefully over here. I called the phi one thing f and the phi sharp thing f sharp. So phi one goes from s to t, and phi sharp for every little s, well, it goes from s times t to s. Phi sharp takes an s and a t and gives you an s. And people often might write this in lenses, lens terminology. They'd write get taking s to t and put taking s times t to s. And here get is phi 1 and put, well, I already said that, I guess. Sorry. So that's just a polynomial map, but what happens if you ask for it to be a cofunctor? It turns out that we would take those things and we would write them out, and we would say that if we take phi sharp on s, on some s of the identity, which is really just phi. So let me try to say this. Yeah. So the identity law says that put of s get s. This is the identity on where s goes. Should be s. So if we come back with the identity on where s goes, that should be the identity on s. So the problem here is that the objects of this thing, what category does this correspond to? It corresponds to the category with s many objects and a single map between every two. And what's happening that's slightly confusing is that there's a lot of arrows. Is that the name of the object and the name of the morphism are being equated here, or they have the same names. And so the name of a morphism might be thought of as where its codomain is. So when we take the identity on get s, that's called get s. And the identity coming back on s is s. So it's kind of confusing, but that's what that's saying. And the codomain thing, number b there, cods, says that when I get the result of when when I get the result of putting S with T, that's T. So it says if I pull back and then I take the codomain, which is equated with the morphism name, and then I push it forward, that should be the codomain over there. Composition says that if I put the result of putting S with T, and then I put that with T prime, that's T prime. And so these three together is called a very well-behaved lens. So very well-behaved lens means these are useful in functional programming and database theory, or so I've been told, and they are just exactly the cofunctors between these comonoids. Okay. Any questions so far?
What about, I didn't know this nice definition of fibration. Does the same thing work for fibration?
I guess if you flip it, discrete op fibration.
Yeah.
If you flip it, I guess. If this symbol maps in, or you put ops, I guess. Yeah. Oh, sorry. The question was, does this definition of discrete op fibration work for discrete fibration instead? And you would use ops. So you would put ops on these guys. A functor from C to D would be discrete fibration if the corresponding functor from C op to D op was an op fibration. Okay. So let's go to number 2 here, comparing and contrasting cat and cat sharp. So first of all, they have the same isomorphisms. An isomorphism of categories is a map from objects to objects, and then morphisms to morphisms, both of which are invertible. But if they're invertible, then you can go forward on the objects and go backwards on the morphisms, and you will get an isomorphism in the language of cofunctors. And so they have the exact same isomorphisms. So if somebody says comonoids are categories, which is something I like to say, they're being a little bit fast and loose in the sense that they don't have this, comonoids and poly don't have the same morphisms as categories. They have, instead of functors, they have cofunctors. But they are the same set of objects. Categories up to isomorphism are polynomial comonoids up to isomorphism. Another comparison is that they have the same initial and final objects. They have the same initial objects as each other and the same final objects as each other, so 0 and y, and the same coproducts. So if you have two categories, C and D, C plus D is the coproduct. Like you literally take the sum of the polynomials, and that thing will be a category if C and D are. And that works for infinite coproducts too. Also, if C corresponds to C, then C set is equivalent to C coalg. We saw that recently. So the functors from C to set are what is this one? This is a set S and a map from S to C of S, such that like when you epsilon out or you do the other thing. I'm going to erase that in just a minute because I want that space. But those are what a C coalgebras are, and so those are C sets. So they have some idea of what each other is talking about in this sort of way. They're friends along this axis. But now that we've done the ways in which they're friends, we're going to go into the ways in which they're very different. And if someone asks me what's better, like cat or cat sharp, what category is really the good one? I have to, of course, say cat. I mean, functors are hugely, like they're all throughout math, they're the most essential, throughout category theory, and therefore basically math, they're the really most essentially like interesting thing. To me, there's no comparison. Now, I once heard Richard Garner, who I respect a great deal, say that maybe one day people will think of cofunctors as important as functors. And I find it very interesting he would say that because like obviously functors are so incredibly important. We're going to show a bunch of ways that categories and comonoids in Poly are different. And in some sense, making cat look like the good one. So let's see. First of all, no opposites in cat sharp. If somebody could, now when I say no opposites, I mean I invite you to figure out how you would say opposites in cat sharp. Like it would be really cool if you could, but what I'm saying is like when you look at n greater than and its opposite is n less than, in categories, that's the easiest thing in the world to do. But in cat sharp, this one is the sum over n in naturals y to the n plus 1. And this one is sum over n in naturals of y to the n, naturals. And there's no relation between those. And moreover, if you have a functor, a cofunctor, C to D, well, I guess I'll write it this way, C to D, does not give, there may not even be a cofunctor C op to D op. So if you can figure out what opposites are in Poly or in cat sharp or something, please let me know. I think that'd be really cool to see. But I find it to be a pretty, like, cat sharp just has no idea what you're talking about when you say opposite, which is kind of strange. There are no equivalences. Like equivalences of categories. Equivalence of categories aren't working right in cat sharp. So remember, sy to the s was the terminal category, a terminal category. It has s many objects, but a single arrow between any two, and that is terminal in cat. So both this and this are terminal in cat. But there is no functor, there is no cofunctor either way. No. There is no cofunctor either direction between 4y to the 4 and 3y to the 3. In fact, there's only a cofunctor if this is a multiple of this. Yep.
So just kind of a prior question to equivalences, is there a notion of two-cell in cat sharp?
There is a notion of two-cell in cat sharp. I guess, yeah, when I was saying that, I was like a little bit worried. That's a good point. There is a notion of two-cell in cat sharp, and we'll get to that when we talk about bimodules. And in some point in my life, I investigated what they were, but I don't remember right now. Yeah, thanks for asking. So I guess there is some notion of, yeah, that's a great point. So categorical equivalence, yeah, equivalences of that's why I wrote equivalences of categories.
The notion of equivalence in cat does not.
Yeah, the notion of equivalence in cat, two categories may be equivalent, and there may be no even mapping between them in cat sharp. Yeah.
Yeah, I was going to ask, I mean, do we know that there's no kind of functor at all between cat and cat sharp?
The question was, do we know that there's no functor at all between cat and cat sharp?
Or a meaningful functor?
There's no identity on objects one. There's no, yeah. Nope. There's something we can do. So, well, maybe I should, yeah, I'll get to something in a minute that's something like that. Another thing that's different about them, no object representer. And this one's for real. Like, I'm not saying like I'm not saying the one from categories doesn't work. I'm saying there is no object representer in cat sharp. And what I mean by that is in cat, we have that obc is functors from the one object category to C. But in cat sharp, there is no C D such that obc, which is C of 1, by the way, would be there's no way to get this. And we could prove that afterwards if anyone's interested. Yeah, I mean, one way to say it is, yeah. Like, what is cat sharp? Just for a quick second, what is cat sharp y blank? If I had a map from y to C, it sends the object of y, the unique object, to some object of C. So if I had some phi in here, phi of the unique object in y must be an object of C with no maps to other objects. It's really a strange condition. It's like it sends it to something, and that thing can have morphisms in as much as you want, and it can have morphisms out as long as they point right back to it. Because if they pointed to somebody else, then those morphisms, when they get pulled back, have to have as codomain that other thing, but there's only one object here. And so we can't have, yeah, so you just can't do it. So it's quite strange. There's no object representer. There's nothing, you can't grab the objects of C by mapping in or mapping out of C. Okay. And something that Nelson will talk about next time is they have very different products, cat and cat sharp. One thing I can say is that C times D is C tensor D. I mean, this is a weird symbol, but if I take two categories and I turn them into comonoids, and I tensor those comonoids, then that resulting thing will be a category, and its objects and morphisms will be C times D. So this symbol is hard to write, but C times D, yeah. So there is a way to get the product of two categories, but it's a tensor product of the comonoids, and it does not have a universal property. It's a monoidal product, and just like before, the terminal category is 1, and that's the monoidal unit there, but this thing does not have a universal property of mapping outs, something like that. Okay. We'll see next time that cat sharp does have products, but they're very weird. For example, if you take this category, y squared plus y, the arrow, and you multiply it by itself in cat sharp, the resulting thing has infinitely many objects. So I don't know. It's like it's going to be interesting. So that's what Nelson will talk about next time. And I don't know if we know whether Nelson, do you remember, is cat sharp Cartesian closed? I think you proved it wasn't Cartesian closed. Yeah. And I don't know if it's monoidal closed with respect to this or not. So there's like some open questions there. Co-pointed polynomials. So a cat sharp is the category of comonoids. A comonoid is a thing with a map to Y and a map from C to C tensor, C composed C. If you just had the top one, that would be called a co-pointed polynomial. And that is monoidal closed. I know that, but I don't know whether when you have both of these, it's monoidal closed. Okay, and the thing I was going to say so at some point, Christian asked, is there any comparison or any functor between cat and cat sharp? And, or any decent one. And of course, between any two categories, if they're non-empty, there's a functor because you can just send everything to one object. But that's not the one you want. So yeah. So one thing that you do have is monoids. Every monoid gives you a category by y to the blank. So at least monoids live in there nicely. They're opposite because on objects you don't care, and on morphisms it goes backwards. But it lives in there nicely. And in fact, this thing has an adjoint, and that adjoint is called gamma. So gamma of a polynomial p, if you remember, was poly py. It was direction fields. Every position in p gets a direction. And gamma of some c epsilon delta will be gamma of c, but it's also equal to cat sharp maps, we said, from c to y to the n. Okay, so you take the free monoid, you push it through here, and you get some, and then you hum into it, and that's gamma. But now set op maps into this. There is a, let's see. I always draw these arrow symbols to tell you the left adjoint. And the reason is because if you start here and then go around trip, there's a map from this to the round trip. And if you start here and do a round trip, there's a map from that round trip back to that thing. So this arrow points in the direction of the unit and the co-unit. But it also points along the direction of the left adjoint. Okay, so this is there's one of these two. Every category, every set has a free monoid, and every monoid has an underlying set. And free is the left adjoint, but for set op, it's the right adjoint. And so there's also poly, and there's maps like this. There's gamma, and there's y to the blank. And every category has an underlying polynomial that sends c epsilon delta just to c. And so if you look at that thing, what it's saying is if you take a category and you take its global sections, well, I mean, it's telling you that that's the same thing as the global sections of the polynomial. But if you stare at this thing, like the thing that, at least for me, what jumps out is there an adjoint there? And that's where we get to number 3 here, Cofree comonoids. Okay. So the answer is yes, there is. So part 3. And what this is going to say is that for every polynomial, there is a category. To every polynomial, there's a category. In fact, we saw one before. To any polynomial p, we had this pp thing. It was like the full subcategory of set op spanned by the directions in p and stuff like that. But that's not the one that's going to be here. That thing is tiny. This thing is absolutely humongous. I mean, it's uncountable usually. And so But now the left adjoints and the right adjoints, either one commute. So if we say let's see, what's the interesting one that I wanted to say? You take them, well, I don't know what's interesting. You start with a set 1. You take the free monoid, you get y to the naturals. Or you get the naturals. You take y to it, you get y to the naturals. That would be, you take y to the 1. So, right, we're getting the Cofree on y to the s is y to the n to the s, like the free monoid on s. I don't know. We can get things out of this if you want them. I guess I'll erase that. It's not that interesting. Okay, so let's construct this Cofree comonoid because it's pretty neat. So the proposition is there is an adjunction. Oh, I guess I already wrote that, but I'll just say it again. There's an adjunction, poly, cat sharp. The left adjoint is the underlying, and the right, maybe some people like to see it this way, so. And the right adjoint is Cofree. But I'm going to write Cofree P as C, like math frac C sub P. Okay. So the question is what, maybe you want to know what, if I take a polynomial and I take its Cofree comonoid, that's a category, and I look at the underlying polynomial, what is it? Or what sort of thing is this Cofree P thing? And the answer is, well, you need to look at what are called P trees. So, well, let me just write it out. Oh, I forgot to say something about this. So, by the way, U preserves colimits. It turns out that cat sharp has all colimits, and cat sharp has tensor. You can multiply two categories, and yeah. But that's not the most important part here. Okay. Well, I guess I also have Cofree of P tensor, Cofree of Q. So Cofree is lax with respect to tensor. So these are some facts if you care about facts. But let's get to what Cofree is. So Cofree, let's talk about P trees. So a P tree is, here's an inductive definition. So CP, so that's going to be what CP of 1 is. And so CP of 1, let me define it co-inductively, I guess you call it. What is an element of this? What is a tree? What is a P tree? Well, it's a choice of position in P. That'll be called the root. And then for every direction there, it's another P tree. And if you ask me what is the directions at one of these, so let's say I pick a root and I pick a tree T for every D, so I can write T of D and get a whole P tree. Then what is this? This is a choice of either the identity or, so 1 plus the sum, you choose a direction, and then you choose a direction in the remaining tree. I'm allowed to write that. Okay. So what is this set of P trees? This is the set of P trees, and this is the directions out of a P tree. Yeah. So this is the set of positions in some polynomial, and this is the set of directions. And later I'll tell you how this polynomial is actually a comonoid, meaning a category. What are its objects and morphisms? These are its objects, these are its morphisms, but what are the codomains and what are the composites and the identities and stuff? So what this is saying, let's say example, I guess I have to block one team or the other team, unfortunately. Example, let's say P is y squared plus y plus 1. And so we would say P looks like this. Then in CP of 1, we pick a position. So for example, we could pick position 3. I'll call them ABC, I guess. You could pick position C, and then for every direction out of it, well, there are none. We do some stuff, but there are none. So this is already a P tree. But so is this one. It starts in position B, and then for everything out, I pick a P tree, and that's an example. Or this one. But then also this one. But also this one that goes forever. Just an infinite binary tree. Or one that does so you can do anything you want. It just says, pick a lowest point, pick a root, which is any of these 3, A, B, or C, and then for every direction, do this whole process again. Thanks. What? Thanks. Yep. Or whatever. Yeah. Or this. Okay. I keep going back and forth about which one's more interesting as another example. So, yeah. I mean, formally, you can get CP as the limit of py, and there's like 2 maps from py, compose py to this thing. One of them is by projecting on this side and getting py composed y, and that's py. And the other one is projecting on this side and getting y composed py, and that's py. So you can just keep going forever. And this is like length 1 trees, length 2 trees, length 3 trees, and you keep going. And this y here is that identity there. That's how those are corresponding or lining up. The fact that it's, yeah. So this is a formal way of doing it if you like formal things. But this is kind of the idea. And so let me tell you, this is the polynomial. I mean, if it's not clear, that the polynomial CP is I in C P of 1, y to the C P bracket I. IT. Okay, that's kind of a dumb thing to write, but I wrote it anyway. I guess I'll erase that. These are the positions, and these are the directions in each position. But then what are the identities? That. And then what are the codomains? Let's say I had a position, I had some direction, which is either the identity or this thing. If it was the identity, the codomain is IT again. And if it's one of these, it's this thing. And if it's something bigger, so okay, let me try to say more correctly. So here are some examples of positions, and a direction in this position, say, this whole thing is one position, and a direction is some finite list up the chain, and then you stop. So in order to get a position, you have to finally end. And, a direction is a finite list up the chain, and the codomain is the tree you get by looking at that as the root. So you come up the chain, you get a new thing. Now, if you picked a new chain of length 23, then you'd get something up. Then the codomain would be that thing. But the composite would be the long thing up to here, and then the 23 more. So it's pretty easy to say what you do. It's just a massive category that's uncountable because, like, you're basically picking, I mean, yeah, it's very large a lot of times. Okay. So that's almost all I had to say. Oh, I remember one other thing. An important fact is that, important to me, and important to anybody who likes coalgebras. So anyone who likes discrete dynamical systems where you're allowed to have inputs that change and stuff like that. Remember, in the beginning we were always talking about these P coalgebras. Or I don't know if we called them that. We called them SY to the S to P. Dynamical systems with interface P. And these, remember, that's SS to P. And then we learned, in fact, Josh told us that that's S to PS. Of course, we already knew this, but we didn't know that this was like a symbol you could write for any two polynomials, but it turns out it is. Anyway, this is typically called, this one here is typically called a coalgebra, and a map of coalgebras is a map from S to T such that P composed, such that this diagram commutes. This is a map of coalgebras. Okay, and so P-coalg is a category. Its objects are P-coalgebras. In other words, dynamical systems with interface P. A set of states. Every state gives some position. And then for every direction there, we get a new state. And the morphisms are basically bisimulations, or things that have, like, for every S and S, we get some T and T where the behavior, observable behavior, is the same. And so the result here is that P-coalg, in other words, dynamical systems with interface P, are equivalent to the category of CP sets. So CP is a category. And CP sets, now this category may be huge, but it's very well controlled. It's given by a finite amount of data, namely P. If P has 3 objects in it, 3 positions and 3 directions, then CP is uncountable and yet defined or presented, or maybe you would say co-presented or something, by just those 3 plus 3 pieces of data. So this CP is huge but very well controlled, and the point is that, like, a CP set and a P coalgebra are the same thing. So for example, let's say P was, oh, I actually have this example written up here. So let's say P was y squared plus 1. Oops. So let's say P is y squared plus 1, y to the red blue plus 1, and S was a 3-element state set with happy, medium, and sad. And so when you're in happy and you do red, you stay happy. When you're blue, you get a little sadder. And when you blue again, you get sad and you don't do any more things. But if you were medium sad and you got red, then you'd be happy again. Then this thing has 3 state sets, 3 things. And basically, in the Cofree comonoid, it would correspond to 3 positions. And those would be that happy goes to happy under red and medium under blue. It just tells you this pattern as an infinite tree. It tells you your entire destiny as a tree. And the point, like, I don't know, I keep saying the point is, this thing is called a topos. And so it has an internal language. And these, the sub-objects of 1, meaning the ones that don't have any, like, so subterminal objects are of this, which are basically these state thingies, like these dynamical systems. They don't have any 2 states that act exactly the same. If they did, we just collapse them into 1 state. If the observable behavior for all time of 1 state is equal to the observable behavior no matter how you probe it to the other state, then we call them the same state. In that case, we would call this thing a subterminal dynamical system. And those are like the logical statements in this topos. And you can or, you can exist, for all, implies, negate, all those different things in the logic of this topos, and understand those in terms of dynamical systems. These dynamical systems, basically, like in this point of view, a position is basically your entire future destiny. You don't know what's going to happen to you, but you know, it's like your character. You don't know what's going to happen to you, but you know what you're going to do given whatever happens to you. It's what you're going to do given the set of directions that someone gives you. So you're looking around the room, you see a clock, you see a person, you see a thing. That directs your mind into some position and pattern. And what it directs you into is the destiny. Like this finite future, this finite little path gives you, from this destiny, gives you a new destiny, like the remaining destiny. Okay, and then I just gave you another, for some reason I wanted to give this other example of a dynamical system. Here P is 0, 1, that is 10y, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9y. And let's say S is a 7-element set, and I have it being this system here. So 0, then 1 goes to 4, 4 goes to 2, 2 goes to 8, 8 goes to 5, and 5 goes to 7 for some reason. Well, I know why. I know why I did that. Because when I was a kid, I was just amazed that 1 over 7 was 0.1428571428. And I was amazed that, like, when you double this, you get this. And when you double this, you almost get this. You get 56. But when you double this, you get 114, and that 1 carries over somehow. And it's just like, wow, how are you doing that? And so I was always amazed that this is one. But anyway, I just felt like I would just draw it there. So this thing, the various places you can start in this dynamical system would give you the various decimal expansions of various numbers over 7, 0 sevenths, 1 seventh, 2 sevenths, etc. And so my point is that, or I don't know what my point is. One thing I want to say is that if this thing is finite, your state set is finite, then in some sense you get what might be called like a rational behavior. So if on this thing, a rational number will be exactly those numbers where this is finite. And so I think I would like to say that a dynamical system is rational. In other words, it kind of like keeps acting the same again and again if it has some finite amount of states. But that's just a personal, I mean, I don't know if it's a good definition or not, but okay, I'll stop. Thanks. Thank you. Any questions? Yeah, Evan?
So you mentioned that discrete fibrations are both functors and cofunctors. Are there other interesting classes like that, or is that what I should think of as like functor?
Yeah, so the question is that I mentioned that discrete op fibrations are both functors and cofunctors. Are those like the only thing that are kind of like that? And that's the only I can think of, because I was thinking, well, for any two sets, there's maps from AY to BY, but those are discrete op fibrations, no matter what A and B are, like for any function from A to B. And similarly, if I have an isomorphism, that's a discrete op vibration. So that's pretty much, wait a minute. So any map of monoids will be a cat-sharpy thing, op. But that's op, so maybe that doesn't help you, because you wanted a map of categories and a map of cat-sharpy things, comonoids in the same direction, probably.
Yeah, I guess that's what I was thinking.
Yeah, but the closest thing is, the only other example I can think of is that monoids op is, yeah. So maybe like sets of monoids. A set of monoids is called a comonoid. Sorry. Anyway, if I have some polynomial and a map, and I have map from P to P tensor P and P to Y, this would be like a comonoid for that thingy. It turns out that comonoids for this thingy, for tensor, are just sets of monoids. Like M1, M2, like 4 different monoids, like y to the M1 plus y to the M2. And maybe there's some more in there. But yeah, it's pretty rare, I guess. Yeah.
So have you thought more about what you can express in the logic of Functors? I've been wanting to talk to you about that.
Yeah, so the question was, do I know anything about what you can express in the logic of this topos about dynamical systems? And I mean, you can do, the problem with like logic in an internal language, what I don't like about the name is that like, they don't give you a syntax and then say like, now you can do anything with this. Like you can do that. You can make yourself a syntax and then you can say, anything I can form with logical statements is my internal language. But usually when people talk about the internal language, they mean like all of the propositions and you can just state any one you want. And so yeah, what are the propositions? They're basically sets of trees. One proposition is a set of trees with the property that any subtree is in your set. If a tree is in your set, then so are the trees you get then so are the trees you get here. So one thing you cannot say is, I am currently red, or I am currently happy, because, because when you do this, you're not currently happy anymore. So it's not the case that being currently happy is closed under going up one unit. One thing you could say is, for all time I will engage in this behavior. Or you could say, I will, let's say you were in this thing, you could say, I will do one for I will do at most a million ones in a row. Or whenever I do 2 ones, I will do 3 4s afterwards, or something. As long as it's kind of a whenever statement.
So it's like invariance versus.
It's invariance, yeah. It's a kind of behavior that that is invariant under anything that happens to you.
Yeah.
So saying I will not do something is saying that for every point I can be in. So let's say you have some proposition, and you say, what does not mean? It says that no matter where you are, there's some path you can do where you can do that proposition. I can eventually, it's always possible for me to do this.
But you said there's a bit of a snag trying to translate, have a global logic for poly in this way, because maps of polynomials would give you cofunctors rather than functors, so that's going to be harder to transfer.
Yeah.
There might not be a nice functor from polynomials to tuples.
Yeah, so given a map of polynomials, you get a cofunctor from CP to CQ, and that gives you a functor that gives you an adjunction between CP sets and CQ sets.
Oh, okay.
But the left adjoint preserves connected limits, but not the terminal object.
Oh, yeah.
So it preserves. So what people might want if they're topos theorists, they might say, I want the left adjoint to preserve, which is this one. It's this one here. I want this guy to preserve finite limits. And I say, sorry, it won't preserve the terminal object, but it will preserve all your other finite limits, and it'll preserve infinite limits. It preserves every limit except the terminal object. You could say, well, it doesn't preserve products. That's true, but it does preserve pullbacks over 1, which are kind of like products. So it basically preserves, all limits except for the terminal object.
That seems like enough to get going.
It seems like enough to get going for a global notion of what logic of poly would be, but I haven't done it.
Have you all written up how it works, that you get that adjunction from a or are we going to talk about it?
We should talk about this. I think we'll talk about it in the course. I don't know how much more time. I'm not sure we'll talk about it, but it'll be in the book eventually, and I'm happy to talk about it offline. Yeah. Maybe we should stop there, Nelson, or? Yep.
Is that related to the biological stuff, or is it a little bit?
Yeah, it's quite related. Yeah, it's pretty. So I'll just tell you very quickly. Cat sharp forms an equipment. The objects are categories. The morphisms are cofunctors, and some symbol we haven't written yet. The horizontals are parametric right adjoints. They're duck queries, or every object